We are taking a page out of the book of VLSI, very large scale integration, which was that transition I think Intel principally made from discrete transistors to integrated circuits. We are doing the same thing with lasers. We're building single chips with today up to 512 lasers on a single chip, 2 centimeter by 2 centimeter laser die. And what this does is it allows you to power tens, 100 terabit per second per chip.
Hello, everyone. This is Sally Ward-Foxton with EE Times. You're listening to our AI podcast, AI with Sally. In this episode, I'm chatting with Nick Harris, CEO of silicon photonics company Lightmatter. Silicon photonics has spent years waiting for its moment, and with AI shifting from a compute-bound to a memory and interconnect bound problem, that moment has finally arrived. In this conversation, we're going to talk about Lightmatter's shift in focus from photonic compute to interconnect, and why the company's new integrated laser represents the next step towards scaling AI infrastructure beyond what copper can support. Here's my conversation with Nick Harris. Okay, hi Nick, and welcome to the show.
Hey Sally, good to see you.
So I think when we first met, for at least 5 years ago now, some people maybe would have thought silicon photonics was a bit of a niche, or certainly an up and coming technology at that point. But today, of course, photonics is one of the hottest areas in AI infrastructure. What has happened in the last 5 years that's really brought this technology into the spotlight?
Yeah, I guess we have known each other for probably 5 years, maybe a little bit more.
Yeah,
We got to know each other, I think, through the AI accelerator sort of boom that was happening.
it's
And
still a boom, some might say. Yeah.
it's still a boom. It kind of like, waned and then exploded again. And now there's all these startups doing that. Um, so what's happened, I think, and it's been a long journey for us. Lightmatter is 9 years old. We were founded out of MIT in 2017. What's changed for us over that time period is people went from, oh, this photonics technology seems to have a roadmap. It's very interesting. It's high performance. But you know what? We kind of have another 5 years, another 7 years of copper and more to squeeze into that. And what's happened in the past, I would say like year and a half, is companies like NVIDIA have made it crystal clear that this is what they're moving to. And the reason is when you look at the racks that they're building, they're incredible pieces of technology. They've got thousands of pounds of copper on the back, and the copper can reach about a meter. So they turned all the servers vertically on their side and made like a bookshelf, so the wires could be shorter. So they're playing every game they can. I think they're even taking racks and putting them like back to back or right next to each other. And they're doing all of this because the copper can't get any faster and longer. So now it's time for CPO, and the whole world is realizing that this is sort of the game to play. And it's a super challenging technology. People talk about, like if you think about the analog world, CDMA receivers for cell phones, like Qualcomm, you think about these companies and how much work it is to go build those kinds of analog systems. Apple had worked on it for a decade or something like that, and Intel tried before. Silicon photonics is kind of like that. It's a very long journey to go from I want to build silicon photonics products to I've had a lot of iterations in silicon. I've worked out all the little tiny minute physical details and it works. And so that's kind of what's changed over the past 5 years for the industry and maybe a little bit for Lightmatter.
Yeah. Yeah. I mean, I know you said copper's reached its limits, but part of the problem, from my perspective, looks like it's just about moving data more efficiently rather than processing data faster, right?
Yeah, I mean, they're kind of coupled because right now AI workloads are partitioned to deal with limited bandwidth. The programs are running on these racks and rows in a way that's somewhat unnatural to them. If you could, you'd like to have the entire row be one coherent computer, but today that's not possible because you taper the bandwidth so much. When you're inside the chip, you're enjoying petabits of I/O. As soon as you leave that, you're in the you know couple terabits, and then when you go at the rack level, it's like it's very low, and so there's this big tapering that happens. What we need to do is get the GPUs to have a bandwidth that's not such a big drop off from what you're doing inside the chip package. And that will allow you to build these giant scale up domains that behave like a single computer.
I think Lightmatter, as you said, started in 2019.
17.
2017, my bad, sorry. Time flies. Over the years, you've kind of evolved. You started as a photonic compute company, but you've evolved to tackle this interconnect problem that we're just describing. Can you tell us a little about that journey and why you've decided to kind of evolve in that direction?
Yeah. So if you go back to 2017, we were focused on photonic compute. We did really groundbreaking research at MIT on what the future of computing might look like in a post Moore's law, post Dennard scaling era. And back then, if we think about AI models, it was about ResNet, image recognition. AlexNet was 5 years before that. And so the whole world was focused on superhuman ability to detect lots of things in images very fast. But those AI models were compute bound. And so if you could build a faster processor, you could have a huge performance uplift. Uh, what happened around 2017, I think the Transformer paper came out that year. And over the next 5 years, what would happen is we would go to LLMs,
Yeah,
transformer based models. Now, transformer based execution, it's not compute bound, it's interconnect bound, it's memory bound. The models are so big, these transformer based LLMs, that they run across tens of GPUs. They're not running on one chip. So, really, they're limited by interconnect. I remember in 2018, I think we had a round, and one of the investors and one of the diligence people were like, hey, this photonic processor is very fast, but I don't know how you're going to keep it fed. And you guys are going to have to solve that. And so we invented Passage back then. And, we've been building that technology since 2018, a year after founding. And it's ended up being like the really big thing to do. And it comes from first principles. The way I see the world in computing is that right now we're going to solve the memory bandwidth and the interconnect challenge. Once you've really taken a big chunk out of that, imagine a pie chart, you drive those to almost zero.
yeah.
So all the time is spent on computing. Now there's room for innovating on computers. And we have an idea about how to do that. Last year, we published a paper in Nature on our photonic computer. And it's also in the chip is in the Computer History Museum in Mountain View, which is like the coolest thing. As a computer geek, I can't tell you how exciting that is. It brought a tear to my eye.
Absolutely. Oh,
Yeah.
okay. So Passage as a technology is just, it's incredibly cool. Can I get you to describe a little more about what Passage actually looks like? What is it and how is adoption going for Passage so far?
Yeah, Passage is our photonic interconnect platform, and it comes in different flavors. We have near package optics, which are optical engines. So imagine a computer chip, but with fibers coming out. And we place it near a processor or near a switch, maybe 6 inches away. And it takes the electrical signals from that processor and switch, converts them to optical, so you can wire up a big supercomputer for AI. So that's near package optics. It's the last time that you're going to have the transceiver, the optical transceiver, separate from the GPU or switch. Lightmatter also builds CPO, and CPO is co-package optics. Here, you are finally shipping every GPU, every switch with the optical transceiver built into the package. Better energy efficiency, better speed, and higher total bandwidth per package. Beyond that, and this is what Lightmatter is really known for when it comes to Passage, is photonic interposer. We have 400 patents in this area, and we've built the largest photonic interconnect chips in the world, up to 200 millimeter by 200 millimeters, so wafer scale photonic interposers, and also our M1000 interposer. And what we do is we take arrays of advanced node chips, think like TSMC N3 or below, and we 3D stack them on a photonic substrate. The packaging tech looks like CoWoS in a way. So you have a silicon substrate and you 3D stack these chips on top. And then they're basically at that point able to communicate using light. And what's really special about Interposer is for the first time, you're not limited by how much IO you can fit on the edge of a die. Computer chips always put the IO on the edge because they're very sensitive little signals. With Interposer, you can put the IO on the entire surface of the chip. That's a big deal because compute scales with area. IO has only scaled with perimeter. So you have something like L squared versus L. And with passage interposer, both things scale with area. So we think this is absolutely the future of photonics and for computing in general. And that's kind of the passage family: NPO, CPO, and interposer.
Should we think of NPO and CPO as like a first gen of this and then the interposer as a second gen, or are they somehow competing with each other in the same gen? Or tell me how you see them versus each other.
Yeah, I think just like with any kind of technology platform or product introduction, you kind of have early adopters and average adopters and late adopters. Right now, NVIDIA is working on CPO. I think that the rest of the industry is going to be doing NPO for the next 2 years while they try to work their way up to CPO. We're also, and this is talking about the early adopters, we're already architecting products with our interposer Passage M series today. And so you're going to see everything exist at the same time. But the average of the distribution will be doing NPO in 27. The average of the distribution will be doing CPO in 28, 29. And beyond that, it's interposer.
So we've talked about CPU, NPO and CPO on the show before, but from your perspective, I'm curious about why. So 2028 in chip years is not that long. This is coming up imminently. But why do you? This has been under development for such a long time. Why do you think it's taken so long, really, to reach this level of commercialization and adoption?
I mean, you had to have a big player like NVIDIA go push the supply chain and have there be such a clear investment that's coming to get all of these test houses and, you know, fiber array companies and optical probe companies and foundries and everybody aligned. You needed that money, dangling, that money carrot dangling. It's dangling now, and everybody's focused on it, and that's kind of what's happened. But there's still a lot of work to do. We're spending a lot of time on wafer level test infrastructure. I'm in Taiwan all the time, working with our partners there, and but we're almost done. It's almost time.
For Passage, though, do you think moving towards CoWoS and other parts of the industry is going to help with that ecosystem kind of already being there?
Yeah, I think with Interposer, you're going to be able to leverage, like, we've partnered with ASE and Amkor, and we're partners with TSMC, and I think all of those companies know how to do chip on wafer flows, so we can leverage that. We've also had to innovate with these companies on detachable fiber solutions. Imagine you put $100,000 GPU on top of Passage. If a fiber breaks, you cannot throw that thing in the trash. That's wild. It'd be like having a USB-C cable on your laptop breaking, and then you have to throw the laptop away. It doesn't make any sense.
Yeah,
So we've
okay,
had to innovate with these packaging houses on how to detach optical couplers from the switch. And we have two technologies. One is called V-Click, and one's called E-Click, and they're both HVM ready.
cool. Very cool. I want to move on to talk about the new laser module that you've been making, but I think maybe we should explain first that to power photonics like this, whether it's compute photonics or interconnect photonics, you need lasers. Basically, it's kind of analogous to the power source or the power supply in electronics. Your new product is a laser module. Why did you decide to build a laser in the first place? Aren't there lasers out there, Nick, that can already do this?
So there are lasers out there, and there are great companies like Coherent, Lumentum, and others that are building discrete laser diodes, and they're literally a diode. So people probably don't realize this, but lasers, typically are a diode, and they're a singulated device. Back in the '60s, when transistors were invented, they were packaging single transistors as a device you would sell, and you'd assemble those on a PCB. That's kind of where people are at with lasers today. You build a single diode, you get tweezers and some glue, and you glue it to a substrate, and you need a lot of them. So to give you a feeling, to power a 100 terabit per second CPO enabled switch, you need 18 laser modules, each with 8 lasers. So you need hundreds of these little laser diodes. We saw that problem, and we weren't, you know, super pumped about it because our first chip on Interposer was 114 terabits. So we would need 20 of these, laser modules, each with 8 lasers inside. We are taking a page out of the book of VLSI, very large scale integration, which was that transition I think Intel principally made from discrete transistors to integrated circuits. We are doing the same thing with lasers. We're building single chips with today up to 512 lasers on a single chip, 2 centimeter by 2 centimeter laser die. And what this does is it allows you to power tens, 100 terabit per second per chip. Earlier this year in Taiwan, we announced Guide 1. Guide 1 has 128 lasers and it powers 50 terabits of IO.
Wow.
Just announced Guide DR. Uh, by the way, Guide 1 is targeted at multicolor DWDM systems. We just announced at our Interconnect event Guide DR. This is targeted at powering 224 gig one color systems. So we think lasers are incredibly important. They represent literally half of the revenue opportunity of all of CPO. So it's an enormous market, and we're selling guide to everyone. Even if you're building photonics, we're happy to sell you our guide lasers, and they have incredible features like self-healing. They're the most accurate and stable lasers in the world, and a lot of other great features.
To be clear, all these or a lot of these incredible features are directly enabled by silicon photonics by integrating, right?
Exactly. So what we do is we build these lasers in a 300 millimeter CMOS foundry, and we have silicon photonics and the indium phosphide gain material. But this is different than how people are building indium phosphide diodes. Those are done in like a 2-inch, sort of wafer fab, and they're small fabs, a couple $100 million versus tens of billions for a CMOS foundry. So the difference in scale here is really quite astronomical. So we can do lots of wafer starts. We have lots of components per chip, thousands, tens of thousands of components per chip. And what that gives us is control, monitoring, telemetry, redundancy, self-healing, all these features. You leverage the complexity to make the system simpler.
Leverage the complexity. I like the sound of that. Okay, one of the kind of most obvious features of your new laser module Guide DR is this form factor, which is completely different. So these are typically pluggables, the lasers, but your module is basically in the bottom of the compute tray. Tell me about the idea behind this new form factor and what advantages do you get from changing the form factor completely?
Yeah, so fundamentally, we're looking at where these laser modules are today, which is the external laser source pluggable form factor. It's called ELSFP. So these modules, you need a ton of them to power 100T. You need like 18 of them in NVIDIA's case. That's a lot. At 200T, you need 36, and it keeps doubling. So that keeps doubling every single switch generation. It's too many things to plug in. It's also too many individual components. And there's this concept called fit rate, failure in time. And what it's measuring is failures per billion hours of operation. When you have a million GPUs in a data center, things are failing all the time. We can't have 100 of these little laser modules plugged in because the technicians, hopefully they're robots, soon, because the amount of work that's going to be associated with just installing, repairing, dealing with these things is absurd. So what we're doing is we're making a new enclosure, a new definition for what the laser form factor should be, and it delivers a 4x reduction in the front of the server faceplate. So you go from something this tall to something like this tall to house the same number of lasers. So Guide DR is powering 50 terabits of IO in a very small form factor. You only need 2 of them for a 100T switch. So this is how we're thinking about it. A new form factor is needed. And we're calling it the laser network interface card, compatible with the OCP rack, tray definition for both the switch and the GPU.
Yeah, I mean, because this obviously looks totally new to me. How important is it to be compliant with OCP standards when it comes to something like this?
Yeah, you don't want to change too many things at once. So you want to take existing infrastructure, existing, sheet metal designs, and you also want it to be something that's broadly available to the industry that everybody can adopt. We want everyone to use this laser network interface card form factor. We think from first principles, it's the right path to go. And we're planning on putting our own lasers, our guide lasers in that form factor.
Can you tell us can you tell us about some of the engineering challenges of moving away from the faceplate? I know Guide DR uses liquid cooling, for example. Liquid cooling, I guess, solves one of the biggest challenges, which is thermal, right?
Yeah, and what's interesting is if you look at NVIDIA systems today, they're already transitioning to banks of 8 or 16 of these external laser sources, and they're inside the server now. There's a little door on the front of the CPO switch, So they're already inside, they're already water cooled. We're just walking that horse one more step to the water, and it's almost there.
I'm curious about whether liquid cooling, should we think of that as a bug or as a feature? I mean, am I still reducing power overall, even though I need so much power that I also need liquid cooling, if you know what I mean?
Well, I think if you think at the data center scale, that there's a metric called PUE, power usage efficiency. Going from air cooling to water cooling, you get a better efficiency, closer to one. One is a perfect efficiency. So just at the highest level, yes, it gives you better efficiency. But there's something better, which is that when the lasers are water cooled, their thermal environment is very stable. And what this means is the failure rates are going to decrease. One of the ways that computer chips fail is when you heat them up and cool them down and heat them up and cool them down, they kind of tear apart over time. There was one, really interesting experiment that Microsoft did where they took servers, put them in like a tube, and put it in the ocean. And what they found is that the reliability of those computers in a tube in the ocean was extremely high, and it was because partly of the reduction in temperature swing.
I saw that Microsoft one. It was in Scotland, I think. I was like, that's what Scotland has, is cold water, right?
There you go.
Um, okay. Do we expect other laser manufacturers to move to this form factor, to liquid cooling? And how standard do you think it will become a standard to have it in the bottom of the compute tray, like we're talking about?
We think so. And,
Okay.
we're working with OCP. We're also leading a separate effort, which is on defining what racks for CPO are going to look like. So we're working with Dell, Quanta, Corning. We win. Every company you can think of in the ODM space is working with us right now. We just submitted the first definition for what the CPO rack is going to look like. That includes the GPU tray, the switch tray, the fiber routing in the rack, and then how you deal with the row routing. So we're really laying out that framework. And we think that the laser network interface card is something that really makes sense for CPO. And, we'll work with our partners.
Uh, I think you said this earlier, but you will sell this to other people who want to buy it. It's not specific to your own photonic stack, right?
Yeah, it's just a better laser for everybody. When Lightmatter pairs guide with our passage photonic interconnect, we can actually get even better performance because we can co-optimize these things. But we're happy to sell it to everybody.
Yeah. Um, Nick, tell me about what you're going to do next. It seems like you're taking on more parts of the photonic stack now with the laser. Could we expect you to go to other parts of the stack, or what do you have in mind for the next few years?
Well, I think one fundamental thing to realize is that graph theory. I'm looking at a data center. A data center is a bunch of GPUs with connections between them. As the data center gets bigger, the number of connections grows a lot faster than the number of GPUs. So the future of computing is really a story about interconnect. Um, I'm obsessed with computing. Light matter is completely focused on computers getting better in a post Moore's law, post Denard scaling world. So today we do lasers, we do interconnect. We have an idea about what the future of computing might look like. We're already working on the definition for what these racks are going to look like. You can imagine over time, photonics is going to kind of find its way into everything and will be central to doing that.
Do you anticipate bringing in your work on photonic compute? I know you said you're still working on it kind of in the R&D capacity at the moment, but do you expect that to become a significant part of the stack going forwards as well?
I think that it could be. I think there are going to be different technologies that people are going to work on once we crush the interconnect and memory access times. Right now, those dominate. So once those go down, innovation in computing is going to be required. We know how to do it with light. We think it's exciting. Right now, the market opportunity on interconnect and lasers is so large. We're focused on that revenue foundation and executing on it. But it's obviously exciting. It's obviously exciting.
It is. Okay, so you're going to be speaking at the AI Infra Summit in Santa Clara on the 15th of September. You're on a panel on day one on the main stage called Feeding the AI Factory, which I guess is going to discuss all of these types of problems and solutions. Can you give us some hints about what you might be debating kind of during that session?
Well, I think that the big story is going to be about how you interconnect these data centers and where things are going for scale up networking and scale out networking. People are adopting near package optics. They're moving towards CPO. There's even people talking about LEDs and VCSELs and other things like this. So I think the conversation will cover some of that. But the future of computing is really coming down to interconnect. One of the exciting results that Lightmatter showed last year was a 3 times faster time to train for the same number of GPUs when they're interconnected by passage. So imagine I've got an existing data center. It's got some power and it costs some amount of money. If I'm using passage, it does 3 times more work.
Unbelievable. Well, I'll certainly be there at the panel to hear more. Nick, thank you so much. It's been a very interesting discussion today.
Thanks, Sally.
Thanks, Nick, for joining us. You can catch Nick Harris on stage at the AI Infra Summit on September 15th in Santa Clara. He's on a panel called Feeding the AI Factory. I will also be there moderating a different panel called Operating Distributed AI and another one about catalysts of AI innovation, which is about AI startups. Both those are on September 15th. So I really hope we'll see you there. I'll put some links on the podcast page at eetimes.com. Thank you for listening.